we're dealing with is a new type of force. And this force is going to be dealing with springs. You solve the problem the exact same way you did before. You draw a free body diagram, you apply F equals ma, and then you do the algebra. A spring force, let's take an object hanging from a spring. So we've got an object, and it's dangling on the end of a spring. And that spring is attached to the ceiling or whatever. What forces are acting on that object? Upward force. Instead of calling it tension when we're dealing with springs, we're going to be calling this force of the spring. F sub s. What other forces? You have gravity, normal gravity. You always have gravity on everything that's on the surface of the Earth, or really anywhere. You always have gravity. And then this time we have a new force we're going to identify as spring force. The spring force? Spring force is pulling us upwards. Because what you do when you attach a mass to a spring is you extend the spring. The spring doesn't want to be extended. It actually wants to pull itself back up. So you get a force upwards due to the extension of the spring.
So when it goes back up, is gravity pulling it back down?
Gravity is pulling it back down. For right now, we're going to talk about springs which are just stationary, though. We're not going to be talking about springs which are oscillating up and down. We'll get to those later on. For right now, we're just going to introduce a new force, Fs. Force of springs. And spring forces are dealt with a law known as Hooke's law. Hooke's law states that the spring force is equal to negative kx. Now the negative just indicates that it's a force that goes back to where it was. A force that wants to pull the spring back to what condition it was already in. So we have a spring here. I think we have a spring here somewhere. Spring. And the spring is in what we call equilibrium position. It's in a position where it likes to be in. If I attach a mass to the spring, it extends out. If I attach more mass to the spring, then it will extend out even more. Now the spring is wanting to pull itself back to where it was beginning with. So if I take that mass off, the spring will go back to its original position. Add more mass, and the spring extends out. So the more mass that I add downwards, the more that the spring is extended, and therefore the more force that it's exerting back upwards. That's what the negative sign is for. The negative sign just says it wants to go back to where it was. As far as I'm concerned, you can leave that negative sign off. It's a confusion to a lot of people because they want to put it in the formula as negative when in reality the free body diagram direction will tell us whether it's a positive or a negative force. Just like gravity. Gravity is downward, so a lot of people want to say negative g or negative mg, when in reality use the free body diagram to tell you positives and negatives. So if you're going to solve this free body diagram, this Fs minus mg, well, I just gave it to you. Sum of the forces is ma. In a static situation, which we're in, there's no acceleration, so sum of the forces is 0. And so when you look at your free body diagram, spring force minus mg equals to 0. Spring force is equal to mg. So whatever the weight is pulling it down, the spring is going to push it back up. What is the K? Thank you for asking. The K is what's called a spring constant. A spring constant is basically how stretchy the spring is. And every spring, a lot of springs will have different spring constants. So we have a mass here. It's a 500 kilogram mass. And we attach it to the yellow spring, and it extends that much. Or 500 grams, rather. Yeah, I couldn't really lift 500 kilograms, so probably a good thing I don't have one of those. So we have a green spring here and a red spring here, and I'm going to put the same mass on both of these springs. Notice that they stretch out an unequal distance. The green spring is more stiff than the red spring. So it's got a higher spring constant. So its K value is higher than the red one that extends more. Spring constant is measured in newtons over meter. So it basically says how many newtons do I have to apply to it in order to stretch this thing out. If the spring constant is very high, then it takes more force in order to extend it out. If the spring constant is very low, then it takes less force in order to stretch it out. X is the distance extended from equilibrium. It's the distance that it stretched from where it was, basically. And that's measured in meters. So to continue this free body diagram solution, Fs would then go Kx equals mg. So the spring constant is how much force was applied and how far did it extend out. Let's just look at a quick example. 5 kilogram mass is attached to a spring. Of constant equals 25 newtons per meter. How far does that string? How far does the spring extend? It's a force problem. We're talking about forces being applied to things. So spring force up. We're going to attach a mass downwards. So here's the situation. A mass attached to a spring, and that spring will go downwards some distance. And then later on, the mass will then be suspended from the string.
So the spring has the spring constant of 25 newtons per meter. I mean, so if you put 25 newtons on it, it'll go up or down.
Correct.
It'll stretch a meter.
If possible. Yes.
So, okay, so I feel like I'm really confused.
Well, this red spring has a spring constant of 25 newtons per meter.
Oh, it's just not.
It's not able to extend 1 meter, and I can't apply 25 newtons of force. You could actually measure this. Here's a force. The more I pull, I can't apply 25 newtons of force to it. Otherwise, it would extend out a meter, but I'd break the spring process. You can overextend these springs, so don't go like hanging from it or anything like that. So continuing on with this problem, when I add the mass to the spring, that spring is going to extend down, and then when the mass is hanging from it, it's going to be at a new position. How far down did that thing go? The free body diagram for the situation is the spring force up and my mass down. So I just solve it. Sum of the forces equals 0, since I'm looking at the situation when it's at rest. Spring force up minus mg equals 0. The spring force is kx minus mg is 0. K is 25 newtons per meter times x minus the mass I've added to it, 5 kilograms, times gravity, 25 newtons per meter times x equals 50 newtons. X equals 2 meters. So if I were to take a 5 kilogram mass, put it on this spring scale, or put it on this spring, it would extend down 2 meters.
So it would break.
Yeah, it would elongate the spring so that it would never go back to its original shape. This isn't designed to go 2 meters. This is designed to go 10 centimeters, which is what we'll be doing in the lab. So really, all it is a force problem. It's a free body diagram with F equals ma, but you substitute kx when appropriate. And you can put springs in any of the situations that we've talked about previous to this. There's a spring on an incline. Woohoo! Yes, I know you'll love that. Other things you can do. You can put masses on top of springs. So it would extend downwards. Right. And now which case would the spring force be in this way? If I put a mass on a spring and that spring compressed, now which way is the force? It's back upwards, because it wants to go back to where it originally was. If I take this mass, I can't take that mass. Oh, close. Close, huh? If I take this mass off, then the spring is going to be extended up to there. Now once I put the mass on there, now the spring gets compressed. So the spring doesn't want to be compressed. The spring wants to be back up to where it was. So in this case, the free body diagram would be spring force upwards, pushing back to where it was, mg down, and you'd solve it normally. In this case, with the incline, the block brought it down. So the spring force would be up the incline, normal force perpendicular, mg straight down, with components. Just like a inclined plane problem, except now instead of, say, friction or another force, we have springs. So it's simply another force added to a free body diagram, solved the exact same way as the other one.